All right. The next concept we're going to talk about is the amount of stuff. And again, this should be a review of things that you've encountered in your chemistry courses before, but we need to go over it just so have everybody on the same page. So when we talk about amount of stuff, we're just talking about a way to go ahead and measure or quantify how much we have of a certain chemical. And one way we can do this is through volume. So volume is simply the amount of stuff we have measured in size. So here I have an example of different containers: gill, pint, quart, gallon, etc. These are all containers in English units, but we might have containers in liters, milliliters, etc. And listed here are common units we may encounter in the course: meters cubed, liters, gallons, feet cubed, centimeter cubed, etc. And these, again, they just measure the size of something. And these should be familiar concepts that you know about. The next concept is amount of stuff as it relates to mass, how much something weighs. And so you're familiar with the scale. Some of us get on the scale daily just so we can know how much we weigh. But the idea behind mass is just simply how much force or pressure, force or something is exerting on something else based on how much material there is. So a scale is simply just measuring that. It's measuring that pressure or force that's being put on based on how much material is there. And so common units that we may encounter are the grams, kilograms, pounds, mass, ton, etc. And this, again, is a pretty intuitive measurement of amount of stuff we have there, but we just need to be familiar with it. Again, how to convert between the different units: grams and kilograms being international units, pounds mass being English units, tons also English units. The next concept is the amount of stuff as it relates to the amount of moles we have. So moles is a way to quantify how much material we have, not by how much it weighs or how much volume there is, but actually the number of atoms or molecules. And it's defined in a very specific way. The mole is 6.02 times 10 to the 23rd atoms or molecules. So if we have a mole of carbon dioxide, we'll have this many number of carbon dioxide molecules. If we have a mole of hydrogen, we'll have 6.02 times 10 to the 23rd hydrogen atoms, etc. So it just tells us the number. And if we were to go in again and count up all the different atoms or molecules, we would find out how many moles we have. Now, there's one concept related to this that is a little tricky, but we have to deal with, and that's the idea of SI units versus English units for the mole. So far, most of your life, you've just called a mole a mole. So when we say a mole, you usually think again of 6.02 times 10 to the 23rd atoms or molecules. And that's actually the SI unit for mole. It's actually known as a gram mole. That's its proper name, a gram mole. But we just call it a mole for short. So when we just say mole, 99.9% of the time we mean a gram mole. We don't call it a gram mole, but we just call it a mole usually. And the reason why it's a gram mole is it's based on units of grams. So we can convert between moles and grams readily by using the concept of a gram mole. And we'll talk about that a little bit when we talk about molecular weight. In English units, we don't use the mole. Instead, what we use is the pound mole. And the pound mole is just the English units equivalent to a gram mole. And we can convert between a pound mole and a gram mole by this number here. So 1 pound mole is actually 453.59 gram moles or moles. And so that tells us that a pound mole is much bigger than a gram mole, or a pound mole is much bigger than just a mole. And if you recall your conversion factors between grams and pounds, it's the number right here. 1 pound is 453.59 grams. And so it's just a way that we can readily convert between pounds and pound moles, or moles and gram moles. So the concept just to remember here is that a pound mole is bigger than a gram mole, and when we convert using the molecular weight, we just have to pay attention to what our final answer is, whether it's in pounds or grams. Okay, next concept, molecular weight. So when we talk about molecular weight, we're talking about converting between mass and moles. And we use the molecular weight. And you've done this before, again, just to review. So if we just add up all the atomic weights, if we look at the periodic table here, go ahead and add up all the atomic weights for the molecule we're studying, and we'll get a final molecular weight. And we can just use that molecular weight to convert back and forth between moles and mass. And when we go ahead and put together and get our molecular weight, we'll have a number that is actually unitless. So the molecular weight of 12 actually implies that the conversion factor is 12 grams per gram mole, or as we oftentimes will just say, 12 grams per mole, and that's what we're used to doing. We're just saying if we have a molecular weight of 12, that it's 12 grams per mole. But a molecular weight of 12 also implies that we have 12 kilograms per kilogram mole. So this is just a kilogram mole is just a unit which is much bigger than a mole, like the pound mole. Or we have 12 pounds mass per pound mole. And so again, the pound mass is much bigger than the gram, and the pound mole is much bigger than the regular mole or gram mole. So if we have something in kilograms and we want to convert it to kilogram moles, we just have to use this particular molecular weight. Or if we have something in pounds mass, we can convert it to pound moles. Now, of course, we can just go ahead and convert using the first one, 12 grams per gram mole, and ignore these other conversion factors. And once we get our answer, if we have to convert between grams and pounds mass and so forth, we can do that, but we just need to be aware that a molecular weight tells us the conversion factor in different unit systems, whether that's SI units or whether that is in the English units. Final concept is mass and mole fractions, and we're going to deal a lot with this in the class. So if you don't know how to convert or work with mass or mole fractions, you need to learn this, because if you don't, you're going to get lost pretty quickly in the course as we deal with mass and mole fractions. Mass and mole fractions just tell us the fraction of a particular mixture for a particular component. So here I just have an example where we have these moles. These are just represent atoms or molecules in this mixture here of A and B, related to the blue and the red. And we want to know what's the fraction of this for component A or component B. And we can calculate the mole fraction. And that's just the number of moles of A divided by the total number of moles. And that'll give us a number. So here's an example. If I have 12 moles of A and I have 20 moles total, that's the mole fraction of A, 0.6. So a mole fraction always has to be somewhere between 0 and 1. It can be as little as 0 or as high as 1. If you're getting a mole fraction above 1 or below 0, you've done something wrong. So it just tells us the fraction of moles. Mass fraction is the same concept, where I take the mass of a component, in this case, mass of A divided by the total mass, to get the weight fraction. And here's an example where I have 12 grams of A, 20 grams total, to give me a total mass fraction of 0.6. So mass and mole fraction is very similar. They just deal with fractions of mass or fraction of moles. Final concept related to this is that the total sum of all of the mass fractions or the mole fractions has to add up to 1. So if I have a mixture right here and I go ahead and add up all of the different mole fractions for the different components, it has to equal up to 1. So the mole fraction of A plus the mole fraction of B plus the mole fraction of C plus et cetera, depending on how many different components there are in the mixture, all have to equal to 1. And this is a formula that we'll use often. It comes in really handy. For instance, if I have a mixture of two components, we'll just say A and B, and I know XA plus XB is equal to 1, and I know XA, but I don't know XB, I can use this formula right here to solve for XB if XA is known. It's just because they should add up to 1. Mass fraction, same concept. If I have the sum of all the mass fractions, they have to add up to 1. So again, we can use this formula to help us out in a lot of problems and solve for unknown variables. So that's it. That's just our review of different ways that we can measure the amount of materials.